Okay, so what we're going to do is we're going to talk a little bit about extending the lesson for equilibrium when you're starting with what's called initial conditions. So previous problems you guys have had have all been under equilibrium conditions. This is going to start with something called initial conditions. So they're going to talk about what happens when you start with a certain value and it's not at equilibrium and it does some reacting stuff and it gets to an equilibrium concentration. And if you remember, equilibrium means the rate forward equals the rate in reverse, and there's no net change in the amount of stuff you have. Initial conditions, they definitely change because they have to get to that equilibrium. And what we're going to do is figure out from the problem and the one value of the equilibrium concentrations how much each one of them changes. And we're going to use stoichiometry, but it's real simple stoichiometry to figure out the other concentrations. And the way we're going to do this is we're going to create something called an ICE table. ICE stands for initial change in equilibrium conditions. Generally speaking, it's molarities. So ICE tables, and I'll show you how to set one up. You want to kind of read carefully. First of all, when you see temperature, I want you to cross it off. Not important. Okay? And I want you to go through and I want you to read the information and say, all right, 2 moles, 1.5 moles, 3 moles, placed in an empty 1 liter container. I want you to recognize this as your initial conditions. And then at equilibrium, this is my equilibrium conditions. Okay? So we're starting with the initial though. And the way you set up an ICE table is you rewrite the reactions. Sometimes people call them RICE tables. Reaction, initial, change, equilibrium. And I want you to draw a line down that separates the reactants from the products. And that's important because the reactants are either going to lose or gain, and then the products are going to do the opposite. So if you read this carefully, 2 moles in a 1 liter container, and we are looking for molarity, keeping in mind molarity is moles over liters. 2 divided by 1 is 2 molarity. 1.5 moles of oxygen in the 1 liter is 1.5 molarity. And 3 moles of SO3 is 3 molarity. Okay, so I've used that information. And it says at equilibrium you have 3.5 moles of SO3. Well, 3.5 moles in a 1 liter container means at equilibrium, which is here, I have 3.5 molarity. And I want you to think about that for a second. What's happening? What this table is showing us is that what I started out with changed. And the SO3 changed by going from 3 to 3.5. So it changed by adding 0.5 molarity. Well, if it's going to gain, my reactants have to lose because that's the only way I can turn products or create products is if the reactants get used up. So that's the first thing. I put the plus sign where the products are in this case, and I put the minus signs on the opposite side of the double arrow. It could be the other way. You could have plus signs on the reactant side and minus signs on the product side. It just depends on the problem. So for the change, we need to do a little bit of stoichiometry, and change is based on the mole ratio. So if I have 0.5 molarity SO3, 2 SO3s are created from 1 oxygen, and I got those numbers right here, mole ratios, right? So I divide that out and I find that the oxygen must have lost 0.25 because 0.5 divided by 2, so 0.25. Now I'm going to do the same thing. I'm going to erase this, and I'm going to erase this, and I'm going to do the same thing to find the SO2. Well, it takes 2 SO3s to make 2 SO2s, or vice versa, I guess. So my SO2s must have changed by 0.5, but it has a minus value, okay? And so the way it works is the initial plus the change gives you the equilibrium. So what I have is 1.5 plus a negative number, which is the same thing as subtracting it. I get 1.25, and I get 1.5. Now I have all the information, and I can set up my KEQ expression. I have SO3 squared, remember, coefficient of 2, over SO2 squared, coefficient of 2, and oxygen. And these guys are multiplied together. So I'm going to put in my equilibrium values, not the initial values, but the equilibrium values go in here. 3.5 squared 1.5 squared, 1.25. When I do that on my calculator, I find the answer is 4.36. Remember, K and Q's don't have units. Okay? And that's basically how you do it. You just kind of have to pay attention to what you're doing. Read really, really carefully. Okay, so let's try this one. Again, I'm going to put my line between the reactants and the products. And I'm going to read carefully, and I see I have 1 mole of SO2 and 2 moles of SO3 in an empty 2-liter container. So this is my initial information. And again, its molarity is moles over liters. So my SO2 is 1 divided by 2, 0.5 molarity. My SO3 is 2 divided by 2, 1 molarity. And then again, temperature, not important. Equilibrium, that's my number. Well, I don't have a number how much it starts, but if you see that word empty, if I don't give you a number for it, you can assume it's 0. So at equilibrium, the oxygen went from being 0 to 0.08 divided by 2, 0.04. So going this way, and again, ice is initial plus change gives you equilibrium. It must have gained 0.04. That means the SO3 lost, but the SO2 also gained, because remember, you put plus signs on the same side of the arrow, you put minus signs on the other side. So it gained 0.04, so now we're going to do our change using stoichiometry. 1 oxygen, 2 SO3s means the SO3 changed by 0.08, and if I put in 2 SO2s, I get the same number. It's 0.08. So at equilibrium, initial plus change gives you equilibrium. I have 0.58 and 0.92. So put it into my KQ expression. SO3 is again squared because it has a coefficient of 2. SO2 is squared. And then the oxygen, products over reactants, 0.92 gets squared, 0.58 gets squared, and the 0.04 does not. Divide that all out, and you're looking for the number without units. And I got 62.9. Okay, so those aren't too bad. When they give you the initial and then they give you the final, you just kind of have to work backwards a little bit and be very careful. That's why I always recommend doing this change thing. Remember, initial plus change is equilibrium, and that you always put the plus signs on one side and the minus sign on the other side, and usually the problem kind of gives you hints in that direction. But what happens if you don't have equilibrium values? Well, first of all, you have to figure out where you're going to put your pluses and minuses, because it's not real obvious anymore. And the way you're going to do that is if you see a 0 in the products, that means you're going to put a plus sign on the product side of the arrow. If you see and a minus sign on the reactants. If you see 0 for the reactants as it's written, you're going to put a plus sign where the reactants are and a minus sign where the products are. And that tells you what you're going to do. And so what we're going to set up now is something called ICEE tables. Initial, change, equilibrium, and end. End meaning the answer. Okay, so sample problem. And again, I'm reading this very carefully, and I see my reaction. I got my K, and I see this. And to me, that is the initial, but I want molarities. Okay, so 1 mole of oxygen divided by 4 is 0.25. 1 mole divided by 4, 0.25. Doesn't say anything about the CLO, so I'm going to say it's 0 to start. So that means it's going to have a plus sign. These guys are going to have minus signs. And the change is based on the mole ratios. Well, I don't have any numbers, so I'm going to have to use variables. And so I'm going to say, all right, well, Cl has a coefficient of 1, so it's going to lose 1x. Oxygen has a coefficient of 1, so it's going to lose 1x. And the CLO has a coefficient of 2, so it's going to gain 2x. Initial plus change gives you equilibrium, so I have 0.25 minus x, 0.25 minus x, and 2x. And so if I was to use my KEQ expression, I would have the, oh, not that, ClO squared, because it has a coefficient of 2, over the chlorine multiplied times the oxygen. And I'm going to put in the equilibrium values. Okay? So what I have is I have 2x quantity squared. Really important to do that. The ClO concentration is 2x and it gets squared. So the 2 goes outside the parentheses. On the bottom I have 0.25 minus x times 0.25 minus x. Okay, so bear with me. I'm going to do a little bit of math thing here. And I'm going to say that equals 2x quantity squared over 0.25 minus x quantity squared. And that equals 156. Okay, so you see what I did? These two terms are the same. I multiplied them together and called them squared. And the reason I did that is because what that gives me now is it gives me a perfect square. Okay, and I don't have a whole lot of room, so I'm going to have to erase some of this to go through and solve the problem. And since it is a perfect square, oh, go back, I can take the square root of both sides. It's much easier to do that than to try and distribute or FOIL this denominator term. And so when you do that, you get the square root of 156, and this is the one thing that people forget all the time, is to take that square root, and it's 12.5 equals, when I take the square root of 2x quantity squared, it's just 2x. And when I take the square root of the quantity 0.25 minus x, it's 0.25 minus x. And so now what I have is I have algebra. Okay, it's a little challenging, but I'm going to cross multiply and cross multiply here. On the right hand side I'll have 2x. When I do 12.5 times 0.25, my calculator says 3.1, so that's this and this. And then I'm going to multiply 12.5 times negative x, and I get that. I'm going to add the 12.5 over, so I get 3.1 equals 14.5x. X ends up being about 0.216. All right, I'm not done with the problem yet. Solving for x is not the solution. I need to fill in that last column, that end value. So I'm going to take the x and multiply it times 2. I get 0.432 molarity. And then I'm going to take this number and I'm going to subtract it from the 0.25, and both of these are 0.034 and 0.034, molarity and molarity. And this is what you want. You want your end molarities. Okay, the answer, that's what they're asking for. Okay, pretty complicated problem. Not terrible, but pretty complicated. Okay, but what happens if it isn't a perfect square? And you're going to run into these, particularly when we start talking about acids and KSP. If the KEQ that you are given is larger than 0.01, you might have to do some complicated math. You might have to do a quadratic equation. It gets pretty ugly. And so we're not expecting you guys to do that. It's not something I even have AP students do. If KEQ is really small, in other words, less than E-2, we're going to approximate the answers. It makes the math a whole lot simpler. So if KEQ is less than 0.01, it means that you have a lot of reactants, right? KEQ is products over reactants. If this number is less than 0.01, that means I have very little products and lots of reactants. And so not much of the reactants actually do their thing. And what that means is that the initial plus the change is essentially just the initial. In other words, you can ignore x in the equilibrium value I plus c. You can just ignore it. We're going to pretend it's just the initial value, and I'll show you how that works. It makes it a lot simpler. So for this reaction, you have KEQ, pretty small number, okay? And in an experiment, they put in the PCl5. Okay, we'll put in our ice table here. Okay, draw the line. This is the initial. It says empty. So this is the initial, and again, you want molarities. So 2 divided by 4 is 0.5 molarity. This is 0, and this is 0. they're going to gain, and this is going to lose. Okay? And the amount they're going to gain and lose is a variable based on their coefficients. So we're going to say x has a coefficient of 1, 1x. Coefficient of 1, 1x. Coefficient of 1, 1x. So at equilibrium, initial plus change gives you equilibrium. I have x, x, and 0.5 minus x. So to put that into my equilibrium expression, I have Cl2 times PCl3 over PCl5. Nothing is squared, everything has coefficients of 1. So when I put in my numbers, what I have is I have 6.4 e negative 3 equals x times x on top, which is x squared, over 0.5 minus x. This is not a perfect square. The top is squared, but the bottom isn't. And the bottom isn't because it has a coefficient of 1. So you may think, oh God, I got to cross multiply and set it equal to 0 and use a quadratic equation. The answer is no, you don't. Okay? What you can do is you can say, I assume that x equals 0 with respect to the initial concentration of my PCl5. So in this case, 0.5 molarity. And what that does is it turns my equation from being 6.4 e negative 3 equals x squared over 0.5 minus x. This part of it goes away because x is 0 compared to this 0.5, and it's going to be, when I subtract it, it's not going to make a difference, so why have it in there? So what it does is it turns it into 0.5. All you have to do is cross multiply, and take a square root. And you get x equals 0.057 molarity. And again, x is not the solution. We need to do the end values. 0.057, 0.057, and then if I subtract it from my 0.5 value, I end up with 0.443. Okay? And so that's what you're looking for. You only need to do this if this number is really small and you don't have a perfect square. Okay, but we're going to be doing a lot of this when we get to weak acids.